It's nice to see so. Buyback, nice to meet you. Is that the first time you joined the call?
No, well, I was there, but like the video sometimes doesn't work properly with the internet. So yeah,
Okay.
yeah,
Yeah,
I've
it's
been there.
Nice,
he's
nice.
based
Yeah.
in Asia, so sometimes it's far
Yeah,
away.
it's also late for you, I imagine. Yeah. No,
But
yeah.
yeah,
Nice. Good to
nice to
see
meet
you.
you. Yeah.
Yeah. Um, yeah, so please feel free to ask any questions that you have with respect to the previous lectures. I differently from the previous lectures today, I'm not going to start with a recap. So like if you have any questions, yeah, feel free to unmute yourself and ask them. In the meantime, let me open the list of papers.
Yeah, I just want to share my thinking about reading the papers in general, a general overview, not specific for one paper. And what I noticed that, if I was reading the paper like 2 months ago without the background that Antonio gave us, that one was going to be like completely unknown. I was not able to understand anything in the explanation of the modeling technique, but at least with the background that Antonio gave us, I was saying, okay, I know what is ReLU, I know what is activation function, I know. Okay, so that one was my the good receiving of the Antonio lecture. So any general view in this aspect?
Yeah, there are a few things that are new, like in these three papers that we're going to be discussing today. And I prepared like one slide in these new concepts, which I think could be like nicer to explore because it's nice to know like what's out there beyond the things that we covered, right? So I think that's going to be good.
Okay.
So no questions at all. Okay.
I might want to ask a little bit about the 1B. I tried using the 1B, and then may I just ask like how do you normally what is the thing that we look for to find the best? Like for example, if we run a bunch of if I run a bunch of different like learning rate and learn if different hyperparameters, and what is the thing that we will look for if we want to choose that one to be our model, because maybe we run 100 simulations and then the one and then what is the I'm thinking that maybe is the test Pearson R, or is there like a parameter that you specifically look for if it's doing regression?
I mean, depend on what you care about, right? Yeah. So depend on what you care about. So for example, if you're just looking for a model that has a good correlation, right, with the ground truth variable that we're trying to model, right? So like if it's just a matter of like good correlation or good accuracy, right? Like I think for the CNN tutorial, we are dealing with the satellite image data set. So like there, it's a matter of accuracy in the classification of the samples, right? If I care more about accuracy, I'm going to select the model that has the highest accuracy for me, right? As the final accuracy, like in the end of like all the epochs of training, right? So that's you guys remember that there is one panel that has a bunch of curves for different number of parameters, like different combinations. So like you can filter using that, right? And then select the model that has the best performance. Then you can see what's the path, what's the name of that model, and go back to the folder where the models are saved and load that model and start using like for inference and testing. So that's usually what I do. But for example, in some cases, let's say that I'm dealing with a self-supervised learning model, right? So in fact, I don't have ground truth label. I'm basically trying to learn some properties about the data itself, right? So like in that case, what I'm trying to evaluate might be just a matter of like, what's the model that has the lowest loss? Because like, I don't have a metric like accuracy, for example, you know? So I select the model that has the lowest loss. But then, of course, then the metric that I'm using for fine tuning, it has to be updated, right? So like you guys remember that the metric was accuracy / validation, right? So like in that case, it would be loss / validation. And then I'm trying to minimize. So that would be the only difference.
Thank you.
Yeah. But if you have any questions about that, like I can show you what I do, but that's essentially what I do. I just go like for what's the metric that I care about, and I filter the model that has the best performance.
Oh, okay. Yeah, I'd love to learn a little bit about the filter after. Yeah.
Yeah.
Maybe in
I
material.
can show you.
Yeah,
Mhm.
thanks.
Yeah. Any other questions before we start? Are all the presenters here, like the people who are going to introduce the papers? So let me see who are the people. I remember that Buyback was one of them. So like he's already here. Then there was Oliver. Is Oliver with us?
Yeah, I'm here.
Excellent. Oliver is here too. And then who was the last one? The last one was Charlotte. Is Charlotte here?
Yeah, I'm here.
Okay, great. So everyone is here. So yeah, if there are no further questions, maybe we start with the papers then. Like I think the most voted paper was the one that Oliver proposed. So that was modeling urban expansion by integrating a convolutional neural network in recurrent neural network. So the way how I want to organize this paper discussion is basically like you guys introduce what's the problem, right? And like what's the problem that the paper is trying to address, discuss a little bit about the data, and then I present the method, and then we discuss the method. Okay, so Oliver, maybe you can go first.
Yeah, sure. I will share my screen in order to see the paper.
Please.
I think it's better like this. Okay, so first of all, this paper uses as a study area a few cities from a specific region in China. I will zoom in order to see the cities that this paper is trying to predict the urban expansion patterns of cities from 2021 to 2050 using four different models. First of all, I'll start with the data. So the input data for this model were the urban land data, which was divided into urban and non-urban. The land use.
Zoom a bit more. Can you just zoom a bit more, just so we can read the things there?
Yeah.
Yeah.
So basically, the
Perhaps
data is from the years from 1992 to 2020. At different spatial resolutions, different from 40 meters to 1 kilometers. Other data categories are the land use types, the digital elevation models, the soil type, the average daily temperature in January and July, and also some demographic data. So basically, they're using convolution neural networks and recurrent neural networks models in order to predict the chance of a pixel to transform from non-urban to urban. First of all, they used the data that I said from 1992 to 2020 in order to validate the model and then to choose the best model to predict for the years 2021 to 2050. I think I should switch to the next page in order to see the difference. The models that they use the UNet architecture for convolution neural networks and long-short term memory for recurrent neural networks, and also the third model was by integrating the two models for the entire region, and the fourth one was to integrate these two models at the individual city level. And as a result, the last model was chosen as the best model to validate, and it was compared with the actual urban expansion. And this one has the best accuracy of all. I think here we have some, there we have the parameters that were used for validation.
Yeah, I think the important part is that we understand essentially what's the problem, right? That this paper is trying to address. And I think you already explained this pretty well, which basically try to predict the expansion of the urban area, like throughout the years, right? And like the way how they split this data is essentially like by training the model, like with data from the 90s to 2010 or 2015, right? Something like that.
20.
And they do the prediction for 2015 to 2020, right?
Yes.
Yeah, right. Yeah. So that's essentially what you're seeing here. Okay. Yeah. So I think the problem is kind of clear, right? Any questions with respect to the problem? That's Oliver just explained to us.
What is the response variable? Which is the range, the gradient of the response variable, the observation response variable?
I think it's a pixel-wise prediction. So like it seems to be.
It's calculates the probability of one pixel.
No. That one is the output. What is the input? The response variable, the input. What is the range? Is a continuous variable? Is a categorical? Go from -20 to +200?
Oh no, all the input data was normalized with values between 0 to 1. Was normalized, yes, from the range to 0 to 1 to obtain the driver factor layers.
I'm not 100% sure. I think it's 0, 1. It's a classification problem.
Yeah, 0 to 1. I think.
Okay,
yeah,
so it's a binomial. Yeah. Okay, it's a categorical variable where probably, let's say, 1 can be any number. 1 is urban.
Yes.
Expansion, so they expanded in that year, and 0 is the agriculture field or whatever is not urban. Okay, because then the probability of becoming urban cannot be where it's already urban. So you need to,
of course,
where is urban cannot be urban again. Okay, so the one that become red in the one was before agriculture or forest, let's say, not urban, and probably not water too. And then you are predicting the probability to become urban. So your input variable is 0, 1, categorical, where the 0 is the whatever is not urban, and 1 is the expansion in that particular year. Okay? It's clear for everybody. Always try to keep in mind, okay, what is my response variable? Which are my predictors and the model technique? Okay, and you can figure out immediately that it's categorical because you see the kappa. Okay, over there, 99% of accuracy kappa, so means that is a classification. Okay. Okay, good. Oh, go ahead.
So I will come back to this part where it is explaining how the data was processed and how they constructed the model. So each of the variable were also normalized, as I said, from the range 0 to 1, and also the drive factor layers were sliced into small data cubes. The data cubes were sliced into 2056 by 256 data cubes with the 75% overlap between two data cubes, and they were rotated by 90 degrees, 190 degrees, and 2070 degrees for the convolution neural networks, and for the recurrent neural networks, the features were selected as a sample. 90% of the pixels of the samples were used as training samples, and the rest of 10% were testing samples. And here we have the architecture of for each model. So you have UNet, as I said, for
I can
CNN.
explain that. Yeah.
Yeah. I think that's better.
Yeah. Maybe we can just go back to like to the data set. To the data sets panel. Yeah. There. Oh, no, sorry. The one below, like in the figure.
Yes.
Yeah, database. Yeah, here, right? So yeah, so like the driver factors, you have distance to the city center, distance to railway, distance to roads, like all these variables, they are like basically layers, right, in your data, and they're already normalized between 0 and 1, right? Okay.
Yep.
And then you have urban land data, which basically is this binary map that says where the urban areas are and where they are not, right? And that's essentially like the data that we're going to combine to give as input to the models, correct? Hello?
Yes.
Yep. Yeah.
Okay, good. Perfect. Yeah, so maybe I share my screen now, then we can go over the method. Let me just close this. Okay, let me share my screen. You guys see my screen?
Yes.
Okay.
Yes.
Great. Yeah. So thank you, Oliver. That was a great like explanation of the methods of the paper with respect to what's the goal, right? Like we understand the data like reasonably well, right? So that's what we're going to be trying to do, right? Like in this paper is to combine this information that's coming from this driver factor data, right, to the urban land data, and try to come up with a method that basically gives us an index of probability for where the urban area is expanding towards, right? So like where, and train the model to predict like these new expansions of the urban area. So like for that, let's break down like into these individual panels, right? So like I think the first one, Oliver already explained pretty well, right? Like that's this stack of like the drive factors in the urban land. So I'm going to skip that, right? He already explained this idea of like breaking the data into smaller cubes, right? So essentially this data has like information of the whole area, right? So like it has a bunch of locations over that. So in order to augment the data and like provide more samples for the convolutional neural network to be trained, right? And that's one of the things that they basically say in their paper. They decide to chunk this data in smaller cubes, right? So like that's the idea of like getting these cubes in is like portions of 256 by 256 pixels, right? With all the layers, so like all the depth is kept, right? This is something that like I didn't cover during the class, right? Which basically stands for like augmenting your data, right? So we did use different types of regularizations for the model, right? Like the dropout, we talked about like weight regularization by penalizing big weights, right? And those are all things that they are meant to first make the problem more convex. So like it favors us to find like what's the optimal set of weights that better like give us like better performance, right? And of course, also we're trying to prevent some other issues such as underfitting and overfitting, right? So like, for example, one of the things that might happen is that this network could get very good in predicting things that they have a specific orientation, right? So for example, let me make like a little sketch here on the top. Is this working? Okay, yeah. So for example, if you have several samples of like rivers that they always go in one direction, right? So because let's say that's like in the big picture, the river looks like this, right? So like now I'm selecting small chunks of 256 from this sample, right? So this model would be very good in predicting rivers that flow in this direction. So like this would be one sample from like one cube that was selected, right? So this would be a model that will be very good in predicting like river, for example, that's flowing this one direction. That's just an example. But in fact, the river can flow in any direction, right? So like one type of like operation that you can use to try to increase the flexibility or how well this model generalized to the data set is to say, you know what, rivers flowing any direction. So I should be exposing my model to rivers that are flowing other directions. And that's essentially the idea of doing these rotations that you see here, right? So now, like, for example, this one sample that you had here becomes another, here they're using 3 different types of rotation. So it becomes like river at 90, river at 180, and 270, right? So like you expand by a factor of 3 using this idea of rotations. Of course, there are more operations that you can do as well, which is like the flipping sideways, horizontal flipping, and vertical flipping, right? Which are like other operations that people use a lot. And funny enough, this is a concept that came from psychology, right? Because the idea, which was also proposed by Jeff Hinton, right? Like the godfather of AI, he said that like, you know, if you show me a picture of a dog, if you flip it sideways, this is still a dog. It's not going to change the concept dog, right? If you rotate, even if the dog is upside down, this is still a dog. So like these models, they should be able to generalize to like permutations as you see here, right? So that was the general idea and it's quite effective. People use a lot. Okay, so that was the idea of using these rotations, okay?
So Antonio,
Okay.
sorry, this one is part of the one of the convolution that we insert in the model. So last time we were selecting different kind of filtering, how they call it, convolution. So this one is another. This one is another one. This rotation, but they will be treated in the same way.
So those are 2 different things, right? So for example, if I remember the example that I had the river, right? So like if the river only shows in this position, what's going to happen is that throughout training, my model is going to learn that the only direction that matters is a filter that basically can detect this, right? So like the only filter that's going to be learned would be a filter that like has like a pattern that sort of looks like this. Remember that you saw several filters that look like this? So like it's going to try to detect lines that are in this orientation, right? So this would be the consequence of exposing our model to just one type of orientation, okay? Now, if you do these augmentations like they are doing here, now you're obliged to learn filters that are also in different orientations. So like now you have to learn a filter that also is in this direction, like another filter that like goes like this, right? So that's the difference, is that like after you do these augmentations, you're gonna force your model to learn these filters as well, okay? Now, where this augmentation is implemented, this augmentation is implemented in the data loader, right? So you guys remember that like in the beginning of the script, what we did was to define 2 data loaders. 2 loaders, right? One was the train and the other one was the validation, which I abbreviate to val, right? When you load that, you guys remember that the loading was conditioned by a class called my data set, because I'm not very creative, right? So like I said, my data set was the function that is going to do what for me? It's going to take the whole data set and batch it for me, like, and separate that in little chunks. When I select a new little chunk inside of that class, my data set, I could say, when you're loading, do this for me, which is basically like select a new chunk of this data set and randomly do some augmentation with it, which like could be doing the rotations, adding a little bit of Gaussian noise to the image, flipping it like sideways, flip it vertically. So like that's where these things would be done. So like every time that you select a new batch, right, and a new chunk of the data, you perform these augmentations that you're describing here. So that's done still in the data loading process. That's not inside of the model.
Okay, so it's at the observation level. Okay, I get it. Yeah, now it's clear. Okay.
Yeah. Cool.
Is it clear
Any
for
other questions
everybody?
here?
Anyone want? Oliver, it was clear also for you?
Yeah, it was clear enough. Thank you.
Okay,
Yeah.
cool.
Okay, so so far we only have explained with like the operations that are done with the data for this UNet. We haven't described what the UNet is yet. It's gonna come in a little bit. So like the input for the LSTM here is just like what is this information, right? How this information is changing over time. So like you remember that like for each one of these pixels, we have all that information with respect to like these driver factor information, right? Like what's the urban land data. So essentially what you're doing for the LSTM is to provide this information at the pixel level and evaluating how that pixel is changing over time, okay? So like now we have essentially what would look like a time series, right? Like on how this urban expansion is changing, right? And not just urban, the urban areas, but also the driver factors. So like we essentially have several time series, okay? And we are going to describe what each one of these methods do in the next slides. Any questions with respect to like what's being done in the data level before we get to the model? Okay, so now we get to the model, right? So like we have said so far that this information is going to be fed to the UNet, right? And to the LSTM. So like I'm going to focus on the UNet first, right? So I don't remember who asked, but someone asked about like taking the prediction back to the image space, right? Because for example, what we have discussed like in the class is essentially how to take the data from the data space, which is here. So here we have like the full image, right? To a prediction or a latent space where we predict basically like what's the class or like what's the value that we're trying to regress, right? So when you're trying to make a prediction, so you have like, you want to have one label per pixel, if you will, right? People come up with this idea of the UNet, which is basically like two CNNs, right? That are back to back. So being one CNN identified here and another CNN identified here. So usually people refer to this one as the contraction. So this one contracts and this one expands. Okay. So let's look at the components that they describe for each one of those, right? So for example, here, you guys see the mouse, right? They say that they are using like for the contraction part, they use the convolutions of 3x3. So like now, although they say convolutions 3x3, I hope this is clear for you guys that this 3x3 essentially stands for what's the size of the kernel that they're using to convolve, right? So you guys remember that like we have the full image, right? And then we are using, remember that now this image is 256 by 256, right? That's essentially what's fed to the model, right? And we have this little 3x3 grid that's being convolved with the image, okay? Very well. So then they say that each convolution is followed by exponential linear unit, which we have seen before, right? You guys remember that there was the ILU. So like we said, that's like for the hidden layers, like usually use ReLU, but these guys are using ILU, and they actually motivate that, which is like that the ReLU has some issues, right? And I don't remember if they list that, but we discussed some of the issues with their rule, which is basically like that's like little discontinuity that you have near zero. So like they say that like ILU trains better. So like that's one of the cases where like people already start adopting that. Okay. So, and then they use max pooling as well. So you guys remember what the max pooling is. So like for a set of like 2x2, right? After you have done the convolution, you get just what's the maximum value that you have in that set of like 4 cells, right? You just extract what's the maximum value, try to reduce even further what's the dimensionality of your data, okay? So now they give more details. There is one thing that we haven't covered, right? Which is like, what's the way of going back like in resolution, right? So one of the operations that you do is called this conv2d transpose, right? And I made this one slide that's basically trying to explain what's the difference. So you guys remember that when you're doing the conv2d, right? So let's explain the conv2d first. The conv2d essentially would get the full image, right? Which had like structure sort of like this. And then I define what's a kernel. So let's say that's a kernel 2 by 2, right? So I get this kernel and I convolve with this image. So like I get this thing first, right? If I have a stride equal to 1, then I move to the right, like 1 position, right? So like I get the second cell, and then I keep doing that over and over again until I convolve with the whole data, right? So that's the convolution. The convolution transpose does the upsampling, right? So like, let's see in this example. So that's the input that you're seeing here, right? And now I'm gonna use conv 2D transpose with this kernel. So you see that, for example, if I get for a stride equal to 1, right? If the stride is equal to 1, I multiply this kernel by this one value here, which is essentially what you see here. 2 times 3, right? It gives me the 6. 2 times the 1 gives me this 2, right? 2 times the 1 and so on, right? Now I do the stride of 1. So like now I do the multiplication for the next value. So like I multiply the 4 by the same matrix, then I do that over and over again, right? This now gives me a 3 by 3 prediction for each one of these values that I convolved with, like in the original in the original data, right? Now you see that I have some overlapping information here, right? So like, for example, the first convolution with the kernel gave me this cell, the second gave me this one. So essentially what I do is to sum all of them, as you can see here, right? Which gives me this output now. So you see that like my input was 2 by 2, right? And my output here is 3 by 3. If I had a bigger stride, so let's say that now I don't have any overlap between the windows, which like for the S equal to 2, right? So like the same thing happens. So like I have this 6, 2, 2, 10, right? Then the second one, now it's being predicted here. And I don't have this overlap. So like actually the summation of them is exactly the same values that I had before, right? So like, which is here directly, right? Now note that I have a 4 by 4. Okay, so that's the way how you do the upsampling. So that's the conv 2D transpose that we haven't covered yet, because essentially what we were doing before was just take the data from the original space, pixels by pixels, all the way to a latent representation, or like output layer that basically has one node for each one of the classes that we care about, right? But here we are doing the opposite. So like now we are going from like this latent representation, this output layer, all the way back to the image space. That's why we need to do that. Any questions with respect to how conv 2D transpose works? Yes, Mulitin?
Hi, Antonio. So
hey.
This is like something similar. I mean, it's not exactly Kronecker product, but it's similar to the Kronecker product. So it's just so if it just multiplies kernel around, yeah. It's but there is also some
yeah.
And those and the kernel values they are learned at the end, yeah.
Correct, yeah. So the kernel here, they are learned kernels. So like, remember that we had a different name for that. So instead of K, we used to call it the 0 1 for like for the first kernel. Then you can have like several kernels according to how many layers you have in the data, right? So like, yeah.
Yeah, so this means basically the network learn how to
upsample,
reconstruct the image back to the original dimensions, yeah.
To the but now the output, right, like that you're trying to approximate, for example, in our case, the output's no longer just the image per se, right? But rather what's these probabilities that's associated to each one of the pixels. Yeah.
Okay, thanks.
That's what we're going to be, trying to optimize. Okay. Is that clear?
Yeah, thank you.
Okay, cool. Yeah. So like another detail that they mentioned there, right, is that they use these skip connections that are represented here, right, like by these arrows. So like these arrows, essentially what they do is to add this representation that I had here to this representation that I have here, right? And that was a trick that people learned to use to deal with the vanishing gradients. That's like we had discussed before, right? So like we try to tackle the vanishing gradients using other approach, which was essentially like by trying to add regularization and try to use an optimizer that was safe with respect to getting stuck in local minimas or local maximas, right? But like the skip connection is another technique that's a little bit more recent, like from 2010 and earlier, right? So that was another insight, is that like if you keep adding the information that you had in the previous layers, right, when you're doing the prediction, you also give another layer of safety, like to the vanishing gradients problem. Okay. And another thing that they do as well that we discussed was the dropout of 0.1. Right, so like you remember that, so like for each one of these weights that we have in the network, we randomly set them to 0, right? So like we make the network not be completely relying to the information that's coming to one node, but trying to like disperse that information over the whole network. And they do say that that was meant for like avoiding overfitting, just as we saw before. Okay. And oh yeah, and then there is a softmax, right, that I almost missed it here. Like, so remember that the softmax essentially maps what's the output of my model to something that looks like a probability distribution. And after all, what they're looking for is a probability distribution, right? So like that's perfect, that's exactly what they're looking for. So like definitely they should be using a softmax. Okay, everything makes sense. Like I think besides the conv transpose, everything else we had discussed in class already, right? So like I hope you guys are feeling pretty confident about the skills that you have learned during the course. Okay, so we covered this, right? Now there is the LSTM, which we didn't cover at all, right? So like this image was kind of bad, so I decided to get another one from the internet. And by the way, this image they copied from the book that I shared with you guys. Remember that there was that deep learning book that I gave the link, like in one of these slides. Like that was the book by Young Goodfellow and was Young Goodfellow and Yasha Benjo, right? So this figure came from their book, and these guys, they don't cite the book at all. So like that's plagiarism. Don't do that. Okay. So okay, so the LSTM, I kind of motivated that very briefly, like 2 slides ago, where I said that essentially what we're trying to do is to build a model that's capable of taking in time series, right? And try to extrapolate for like unseen data points, right? So that's essentially what the LSTM does, right? The general architecture of the LSTM, so like let's discuss that first, right? The LSTM, so this is one cell, right? What you guys are seeing here in green, right? So that's one cell of the LSTM, but you can also think of the cell as being like one LSTM layer. Okay, so that's one LSTM layer. And what you do is to stack several of these layers. So for example, here, you'd come with like another cell that looks just like this one, okay? And then you keep like feeding this information through all these layers, right? And with the hope that you keep learn to use information that's coming from the previous time points. So like this time point xt, right? The next one would be xt plus 1, right? So like that would be the difference from like that's xt here, and then you try to predict xt plus 1 as the next time point. Okay. Now let's see what are the inputs to this. So here, what we have, it's H is usually characterized as the output of the previous time step, right? So like what the model has learned with respect to the previous time step. Here you're combining the information that's coming from xt, so like that's my current time point, right? So if you can put that in perspective, let's put this time series again. This would be xt minus 1, for example, right? And let's say that the next one is here. So that's xt, right? So if I feed this information through my LSTM, right, that's going to generate ht minus 1. So that's the output of my prediction for xt minus 1. Now, when I move from this time point to this time point, right, in xt, now I'm going to incorporate this information, xt, right? And now I have to pass this information, that's like the combination of the output of the previous time step with my input for the current time step, right? Through these gates. So like then I have one gate that's called the forget gate. Essentially, it's gonna learn how much information from the previous time step I should incorporate for me to be able to make a good prediction for the current time step, right? So remember that XT in this case is essentially all this information that we have with respect to like what's the current urban area boundaries, right? All those driver factors that we had discussed before. So those would be XT. And the output would be essentially what is the probability of the urban area expanding or like moving a different direction per pixel, right? For the time step T. Okay, so that's essentially what the LSTM is doing here for them. So the forget gate tries to learn how much of the information from the previous time points should be discarded, okay? YT here and the CT is learning how to combine the information that's coming from this stream, which is the input now, right? Is the combination of the current information and the previous time point information. How much of that should I keep as being like important for like broadcasting to the next time points? So like this is, if you will, like some sort of momentum, right? Like how much information from the previous time points I should like keep broadcasting forward, right? And that's essentially what this YT is doing for us, okay? The actual output is passed like through OT, right? So like OT is this information that's now like combining information from CT and the information that's coming from the previous time points, which is in this channel here. Okay, now if you look at that, right, I said that this is one LSTM layer, right? This thing that you're observing here in green, right? Each one of them can be broken down as being their individual networks, right? So you see that's like, I have one network for IT, right? You guys remember that the general formulation of a network essentially is like, how do I learn some new weights, YT, right? That multiplies my input data, and then I had a bias term, right? Look that the input data now is the combination of the information from my current time step and what came from the previous time point, right? So like I'm combining the two of them, learn a set of weights that basically is going to tell me like how much information I should keep, correct? And passing that information forward. So like you see that each one of these gates that you're describing here, they basically act as like individual networks that compose one LSTM cell. Okay. So that's basically like a crash course on how LSTMs generally work, right? So like, I think the important take-home message here is how they operate, which is basically like combine information from predictions of previous time points with the current time point, right? And learning how to leverage that information to make an accurate prediction with respect to like what is the probability in their case of the pixel that I'm considering right now, because remember that this prediction is being done per pixel over time, having an increase or decrease in probability of becoming an urban area, okay? And inside of that, now essentially you have these 6 networks that are described down here. Those are their equations that are trying to leverage the information. How much information I should keep with respect to what came before, how much information I should forget, right? And like try to leverage that to make a better prediction for these probabilities. Any questions with respect to the LSTMs? This was all done very fast, right? Like I think the previous year, I had the in-person class in Matera to be on LSTMs. And then basically we explained the LSTMs and made some experiments over like the span of like an hour and a half. So here, just explain the LSTMs to you in 15 minutes, which is like, yeah, it's a lot of details, but I hope you managed to get like the overall idea of LSTMs.
Yeah, I want to point out that the video was video recorded, so that you have the lecture from last year that you can follow. I will post
great.
the link,
yeah,
the link over here, and from the spatial, is in spatial ecology, so you can figure out. Even if you type LSTM in the browser, you can find it.
Awesome. Yeah. So now we are in the integration step, right? Where they say that to integrate the results of the UNet LSTM, they simply employ this weighted sum, right? So like now they are learning how to weight the prediction right, of the LSTM, because remember that the LSTM is making one prediction per point, right? So like in blue here, you have these predictions, right? And you have the UNet that's basically also try to predict this information with respect to probabilities, right? So like, how do I combine the two pieces of information that are being provided, right? So they learn, they do mention what was the method that they use to do this refining of the weight, but at this point you could use absolutely anything. You could even use like some sort of linear regression if you want, right? Where you have the information like probability given by UNet and probability of LSTM, and then just learn what's the weight of the two that you need, right? So like anything could be used as a way to integrate the two. And as Oliver had mentioned before, right, they did two experiments. So one that basically makes a prediction for the whole region. That's this first equation that you have here. And the second one, it's a prediction per city, right? Which basically implies that the combination of the factors that you're taking in, the driver factors and the information of urban land seems to be specific for per region. So like apparently you don't manage to get one model that explains the urban expansion for all the regions, right? Which is kind of an interesting insight if you think about it, is that like there is no general rule that's being applied for all the cities, but each city apparently has its own rules, which could be conditioned by several factors that probably you guys can think of, right? So like, for example, what's the type of industrialization through which that city is going through, right? Like maybe some types of like urban expansions because of the type of economy, right? Is conditioning how fast the urban expansion takes place, right? So that's a cool insight that they had there. And then of course, like now we have this map, right? That is giving us this prediction in blue for like what are the pixels that most likely are going to become urban areas in the next time point, right? And they translate that to this sort of heat map that you see on the right, right? Where you see like the original urban area in this like pinkish color, right? And what's probably they have a threshold at this point, a threshold that basically says like if it's above that probability, consider that as like now this is a new urban area that was added, right? And that's the binarization process that they do at this step. Okay. And then Oliver mentioned about these comparisons that they did, right? So for example, they do these predictions for like how the urban expansion is going to look like for the next years, right? So they do this prediction for going from 2020 to 2050. All of them sort of plateau, which is interesting, right? Probably is because there is no more place for you to keep growing. Like you're bounded by like the physical boundaries. Like you have the ocean, you cannot build stuff on the ocean, or like you cannot build stuff like over other cities that already exist. So like probably that's the capping that they are observing there, right? And that's cool that they also compare to other methods, right? So like they compare to this FLUS method and LSD urban method, right? And they report that they have better accuracy by most of these metrics that they consider against the other methods. So it's kind of cool, right? So like using two methods that are relatively simple. So like the UNet basically is like these back-to-back CNNs, right? And a third one that we haven't discussed, but basically is trying to model this the dynamics, the evolution of the data per pixel, right? They managed to outperform these other methods that I particularly don't know, but like it's kind of see like how simple the method is, and already achieves like pretty good performance, like 97, 98, 99% of accuracy. Okay, any questions with respect to that before we move on to the second paper?
I have a small question regarding the combination. Hi everybody. Regarding the combination of two or maybe more methods that you showed us before. So when we train some model, even simple one like you mentioned, linear regression, to find these weights, which we apply to different models in this combined calculation. So should we, when we train this model, use different like data set or maybe different test data sets than we used when we trained this input, like models like this neural network. So we should choose maybe another like new test data set for this to be like independent, or if I'm clear with this, you understand what I mean.
Mm-hmm. Yeah, I think I understand the question. Which is basically like, now that you have trained these two independent models, right? And you're just trying to find what's the weight that you should assign to each of them when doing the integration, right? Should you be doing that in exactly the same data that you use for training, or should you be like finding this weight combination already like in your target data set? And I think the answer would be like, you should be doing that in your training set. You can imagine that essentially what you're doing is still fine tuning, right? Like how you should leverage the information that's coming from the two methods to better fit the data that you're seeing in your training set, right? So that's still part of the training process. So you shouldn't be doing that right in your test data set. Okay?
Okay, thank you.
Mm-hmm. Let me check the chat. Okay, so that's Pepe.
So anyone, and especially Oliver, that was selecting the paper, and also for the other that have been selecting the paper, is a bit more clear. Oliver, do you?
Yeah, definitely. Yeah. Not at all, but thank you very much for giving me more insight about these models, because in fact, when I was checking those graphs, I wasn't able like to understand like very much the details of the, for example, for the long short-term memory. It was not clear enough for me to understand those the meaning of each element on this graph. But after your presentation, yeah, it's much more clear on how they applied this model. Yeah, so thank you.
Yeah. And Pepe posted the
post the link with the
link to the video. Yeah.
From last year, the descriptive procedure, and also the video recording.
Yeah, so you can play with that. Yeah.
Okay, cool.
So it's 11:56 for me.
What is the main shortage of the long LSTM here? Is there any, because the advantage will be that you can consider the prediction in the past time step, right? But what is the main shortage if compared to the convolution network? So it will still have to kind of add a weight to the traditional CNA.
It was cutting a little bit for me, so like I'm not entirely sure if I understand the question, but I'm gonna repeat it and let me know if I got it right. So you're saying like, what's the advantage of using LSTM versus UNet?
Yeah, kind of like that. Yeah.
Yeah.
What is the, and also the disadvantage if there's comparison?
Also what?
Also, what is the disadvantage? Like, is there any pros and cons of
disadvantage? Yeah, I see. Yeah. So like in fact, I think that Oliver hints to that, like when he was showing the paper. I think that at some points they do this sort of ablation test where they show what's the performance that would achieve if you use just each one of these methods, right? So you see that like if you can you guys see? Let me zoom in a little bit. You see this plot here? So here they are showing like what happens if you just use UNet, right? So you see that the accuracy was like 99.16 for just UNet. Just LSTM was 99.09, right? So now, if you do the combination of the two of them, right, which is the integration, right, for region-wise, there is no much benefit. So like basically the performance is just the same as of the UNet, right? So you see that like it's basically the same performance here. But when you do that like per city, actually there is an improvement in combining the two of them. Sorry. So yeah, so like apparently incorporating information that's coming from past time points, right, is not as relevant as like trying to understand what's the dynamics of like the urban area that you have neighboring pixels, right? Which, for example, the LSTM is doing this prediction per pixel. So essentially just trying to leverage this information that you have with respect to the driver factors and the urban area, right? So if you think like what's the contribution of urban land data like per pixel, is essentially like a binary variable, which is like not urban, not urban, not urban, and then suddenly urban. So like that information doesn't really help you much, right? Because if you're making use of that information only, right, it's like the prediction should be just flat all the time. And then suddenly there is a transition and you still don't understand why that happened. The driver factor could be more impactful, right? But apparently there are more things that matter. So for example, what's the information that having your neighboring pixel seems to matter the most, right? For example, if you have one pixel that's super far away, like what's the current urban area, right? You know, most likely that's gonna be is still not urban, right? Now, if you have something that's like sort of in the border, let me go back to this. If you have one pixel that's sort of in the border, right? Like with a bunch of other pixels that are already urban area. So you know that like, oh, there is a really high chance that like this pixel, the next iteration, the next time point is going to become urban too, right? So like you can see that the spatial information seems to be more meaningful, right? So I believe that would be why the UNet it's by itself is already like more meaningful.
Oh, got you. Thank you.
Mm-hmm.
Any
other questions?
I just was adding, Samuel, this LSTM is very well used in flow dynamics. Yeah, in flow discharge modeling, because you know if you have high flow the previous day, you will have again high flow in the next day. So it's really time dependent. So there are 3 or 4 papers from a German guy that now doesn't come to my mind the name, but he has been using LSTM. And actually, I think I showed also to Antonio, it was a simple LSTM, according to Antonio, nothing crazy, let's say. It was something simple. When
most of these papers that are like, they're in the application level, you know, like, and then you see several cases like this, like when it's a paper that's focused on the application, usually the model it's extremely simple, you know, because people care more about like what this model can do for me than actually making a model that's like it's more elegant, managed to extract more meaningful information about the data. If you get 99% of accuracy in predicting something that you care about, if it's 99.8, right, like after you do like a more complicated method, you don't care that much about anymore, you know, like, so like most of these papers in geospatial data and like simple like healthcare data, usually they're extremely simple models. And you're going to be completely able to understand what the model is doing based on the things that you have discussed in class.
Yeah, and the same thinking you can see from the geocomputational modeling, from the geocomputational part of it is not really heavy in that context. So many papers you can see that there is not so much data from the geocomputational part that has been treated, and also later on the modeling procedure is quite straightforward. Okay. So there is a plenty of space to grow in the two aspects. Geocomputation has a big amount of data and processing procedure, plus then later on entering in the machine learning with massive data and new method to extract important features. Yeah, this is where this course is trying to go, to bring you guys in thinking that direction, you know. Okay, very good.
So let's do the following. It has been an hour already. Let's do a quick break, and so then we come back and
we can come back.
Then we discuss the 2 papers.
20.
What time?
20.
20.
Okay. 15 minutes.
Sounds good.
Thanks, Antonio.
Okay.
Okay, so we have the next paper. Which one is, Antonio?
That should be the convolution one. So the name was Convolutional Neural Networks Improve Species Distribution Modeling by Capturing the Spatial Structure of the Environment, which I think Vivek is presenting, right?
Okay, go, Vivek.
Sure, thanks. So yeah, so this paper tries to see how the local landscape structure might impact the species distribution model. So they talks about like how the ecological niche is quite complex, multidimensional. So what they have hypothesized is so in the paper they talk about like how the influence of the habitat availability, spatial heterogeneity, and spatial structure around the environmental location might the CNN might be useful to predict with the higher ability. So for the data set, they have used kind of like 4,500 plant species, different plant species with around 97,000 occurrence in France. And for that, they have used around 33 environmental variables. Yeah, and talking about, and they have also compared the CNN with other random forest and boosted trees, and regarding like some of the results, like they have found, they have done a quite a good prediction with mostly with the rare species than the frequent species, so which makes a very they make a case where it's important for the conservation implications in the future. And so the reason that I was interested in this paper was like I was working with the dolphins, river dolphins in Nepal, and I was thinking if this could be, you know, like useful for me, would be helpful for to understand the species distribution modeling of the dolphins. So yeah, that's what I got it from the paper for now.
Nice. So one question here. Did they train one model per species in this paper? That was kind of unclear for me.
So what was the question?
Did they train one model per species, or they train one model to predict the distribution of all these species?
I think one model for all the species, I think.
Yeah, it was not very clear to me. I was trying to understand that from the paper and I couldn't. Okay, yeah. But I think
Yeah,
we got the general.
So once again, what is for Vivek? What is the response variable, the species, but treated in which way? I think I understood actually with something that we also covered last year, but I want to double check with you guys. And there is someone else, please.
Like you mean the species occurrence?
Yes, the species occurrence. Yeah, but how they, okay, a species is 0, 1, presence absence.
Yeah.
But over there they have many species. Okay, so how that's where goes the question of Antonio. They make a model for each one, or they make a model for all together. And in case all together, what is the response variable that feed inside to the model? Yes, species, but treated in how? No idea.
I'm not sure.
Okay, no, anyone want to join the discussion?
That could be as a about binary variable like species presence and absence, or maybe some kind of species. Oh yeah,
yeah, but
usually.
Yes, but this is if you have one. If you have many.
But could we have like a multiple response variable, right? For example, output layer with several like outputs, each of which relates to different species like this. So the one common like neural network, but with 10 different like outputs. Is it possible?
I think the model species richness. So Antonio, what do you understood?
So my understanding was that essentially they're trying to predict this as a probability distribution, right? So like the ground truth is if they do find species in that region or not, that's the ground truth. So like it is a 0 and 1, right? Per species. So like you'd have a map like this per species. So what wasn't, so this part is clear to me, right? Is that like it's a 0 and 1 per species, right? Now, if they train one model to predict all the species distributions all together, that was unclear, right? So like that's the part that I was trying to understand now. But what they do is basically get the model to spill out a probability distribution of finding that one species, right? And then they compare the distribution of these ones in the map, right? So like that's why they use cross entropy. So like essentially what this thing is doing is to compare two distributions, distribution of like ground truth values, the ones versus the zeros distributed over the map, right? With the probability that's being delivered by the CNN in this case.
Okay.
Yeah. Okay, but I think the
Vivek, did you also try to read also the supporting material?
No, I didn't, sorry. Yeah,
Okay.
I just like got it yesterday. I started reading yesterday.
Okay, no problem. Okay, go ahead, Antonio.
But different species always have different like ecological requirements. So it's impossible to have the same model to be applied to different species because like these weights and like biases should be anyway different for different species because they have different ecology.
There are some way, but let's see what Antonio figure out from the method, and then we can see if there is this is what I think that they are doing is correct or not. Let's see.
Yeah. So let me share my screen.
Yeah,
Then
go
we
ahead.
can discuss. Okay. All right. So few things that I think it's interesting to point out that they write in their introduction, right? So like when they're motivating the use of convolutional neural networks, you see that they say that a specific property of CNN is that they rely on spatial environmental tensors, right? Which is like essentially what we have discussed before. And the other methods, they try to do these predictions of these environmental factors, how the environmental factors for one specific location, right? They might be predictive or not of the occurrence of a specific species in that location, right? And essentially their insights that combining this information over space, that might provide more insights, right? Which like that was the same idea that we use to basically pitch in the idea for using convolutional neural networks when you're dealing with image data sets, is that there is more relevant information in space versus just the information that's coming from pixels, right? So it's interesting that they mentioned that in there. And then they say that like capture richer information than in punctual vectors, where the punctual vectors in this case would be the information that you have for that specific location over all the layers of data that you're dealing with, right? Which we're going to be discussing a little bit. Okay, so with respect to the data, right? So like Vivek basically already described that, but the data consists of this for any given position, right? They give these environmental variables that you're going to see in the next slide, which defined in this matrix of 64 by 64 pixels around that position, right? So like that, given the position that you care about, you're evaluating how these environmental variables, they're changing for a radius, like around the position that you care, right? So these matrix of the environment are aggregating to one-dimensional vector, right? So like you have this one patch, right, where you have the 64 by 64 pixels, where the central location is the one that you care about, and then you have this 77 environmental layers, right? Which we're gonna see in the next one. So like imagine that our input data is very similar to what we had before, right? It's an image where the stack essentially is all these different environmental information that you care. Okay, so here's a couple of examples that were in the paper, right? So here we have the information of altitude, I believe, then you have like all this CH bio, which I think we also use for the tree height, right? So those are like, I'm not entirely sure about the others here. Like if there is anything relevant that you guys would like to discuss, probably Pep would be more capable of answering that for you, right? But for all that matters for me is essentially that they describe some environmental features that like are relevant for the problem that you're dealing with here.
Yes,
right?
I'm sorry, but I suppose they're related to bioclimatic variables, like for example, average annual temperature, precipitation, and temperature of the warmest months and whatever. There are a set of usually used like bioclimatic, yeah.
Right. They do mention like what in general these 33 environmental raster variables they stand for, right? So they say like soil, elevation, land cover variables, predictors, and so on. So like I don't know which one is which because they just say like CH bio.
They do in the table 1,
9.
I think, Antonio. Like as Alex told, it's about temperature, like mean temperature of driest quarter, precipitation of driest month, something like that.
Okay. So they do that in table 1. This table. Okay, yeah, excellent. Very good. So like now we know what each one of them stands for, right? Then let me share the screen again. Okay. They say that they split the categorical land cover variable into 45 different layers. So probably this is more clear to you guys, right? So, but essentially what they did here apparently seems to be like this categorical land cover, right? For each one of them, you have like these ones and zeros where basically you just say where that specific type of like vegetation, I believe, is like within that map, right? I think that's what this thing stands for. So then they combine these 45 different layers, right? That now is just like ones and zeros to these 33 environmental raster variables. So like that stacks up to like 77 layers. So that's where this 64 by 64 by 77 is going to come from, like for the data that they're using. Okay. Then they say that the model that they're using is this Inception V3, right? Like, which is a thing that we didn't cover in principle. So I decided to make like 2 slides here that basically explains what the Inception V3 is, right? So you guys remember that when we were doing convolutional neural networks, right? What we were basically doing there was to say like, oh, I have an input image, right? Then I'm gonna do a convolution, right? Like in a small with a smaller kernel size, and then project like to this smaller volume, right? And then from there, I'll do like another convolution with like another kernel and keep like decreasing the size, right? You guys remember that the kernel, right, which is essentially like this little window that I use to convolve, usually is much smaller than the image per se, right? To the point that like, for example, in the previous paper that we discussed, this image was 256 by 256, and then we are convolving with like a kernel of 3 by 3, right? So like it much smaller than the image. So what happens is that when you have like such a small kernel, like the one that like we use in the previous paper, sorry, when you have such a small kernel, right, you're just paying attention to features that are extremely local, right? So like you don't have that much information about like the big picture, right? And like features that seems to be more global, right? So one of the things that these guys in the Inception V3 they wanted to do is like, wouldn't that be nice if instead of like applying these kernels with fixed size and basically like just changing the kernel size for the next layer, wouldn't it be nice if I actually do that in parallel? So like I have a kernel that has this size, but like for the same image, I also have a kernel that's slightly bigger, right? kernels that are also smaller to pay attention to, even like smaller, like more local features, right? And that was basically what they wanted to do. So you see that like here, previous layer essentially stands for like what's the information that's gonna come from the input, for example. So like in this case would be the input, right? The original image. What they do is basically to broadcast that information to a couple of parallel streams, right? Where first you have these one-by-one convolutions. So like one-by-one convolutions, as you guys can imagine, is going to be just like a pixel-wise, but remember that the pixel-wise is being applied over all the stack, right? So like, even though it's one pixel, I'm actually incorporating information from all the 77 layers, right? So that's the layer that's going to be like learning how to mix or how to combine the information that's coming like from all the 77 layers for one specific pixel within this image of 64 by 64, right? I have this other one that's just one-by-one convolution. These guys here, they feed in to like this 3x3 convolution and this 5x5. So like that would be the idea of like a small kernel and then big kernel like running in parallel, right? So like I pay attention to local features, and then I have this would be local. These would be like semi-local. So like that's slightly bigger, right? And then I have this other one that actually does a pooling operation first. So like it takes like a set of 3x3, right? Does the pooling operation, and then does the one-by-one convolutions. And then I have this one that just does the one-by-one convolution, which basically you can consider some sort of skip connection that you mentioned before. This one, I don't remember exactly why they had this one going parallel, but most likely is to avoid the vanishing gradient issue that we mentioned in the previous slide, right? And then after you have done that, right? So like the sizing, all this, after all these stacks is going to be combined into this filter concatenation, right? So like now this information that's coming like from the local information, semi-local information, right? The information that's coming just from the mixture, of lower spatial resolution, the mixture of the lower spatial resolution of the 77 variables that we care about, and the actually 77 combination of the 77 variables, right? Then they're going to be concatenated here and then compose just one variable that's going to be broadcast to the next layer. Okay, so you guys see that like this is slightly different because now you're getting more information from the same step in the network, right? In this case, it would be from the input image, but you can reproduce that for any other intermediary layer that you have in your network. Okay, so that's essentially what's the overall idea of the Inception V3. So like now with respect to sizes, maybe I can step out a little bit here so we can zoom in. Let me zoom in here. So probably this is the network that we have discussed the most, which is I think like this. Yeah. So you guys, that's the type of architecture that we have discussed the most, right? So which is like you have the input image, right? So then you have like convolution, max pooling, convolution, max pooling, all the way down here, where finally after a series of like convolution layers and max pooling operations, then you have the fully connected layers. You guys remember that, right? And then finally a fully connected and softmax, where you project it like to the space that will actually make the prediction. And since you're using softmax, that implies that you're like getting a probability distribution over the nodes that you have in the output, right? So that's the architecture that we saw before, right? Which like for this specific combination of layers here, that there is a cool name, like this is the VGG 16 and VGG 19, which is slightly bigger, right? But that's essentially the CNN architecture that we discussed in the previous lectures. Look that the Inception V3 is much bigger with parallel streams, right? So like the beginning here is like for the Inception V3 specifically, is this field 224 by 224 RGB image, which is followed by like a couple of convolutional layers, right? Max pooling, 1D convolution, and then you have these parallel streams of information that you mentioned, right? So like just the one by one fit into 5x5, 1x1 to 3x3, and then 3x3 again, and so on, right? Then you have the concatenation, and then you repeat the process, right? So you see that's like this extraction of like local versus semi-local, or like perhaps even global information keeps happening over and over again throughout the stream, right? And in fact, like here, I also add like some other architectures that are kind of popular as well in this slide, which is called the ResNets. Oh God. Very slowly so I don't skip slide. So the ResNet is this combination here, right? Which is still one single stream, right? But instead of having like parallel streams of information like they do in the inception, what the ResNet does is to use more skip connections, right? So like remember that the skip connection managed to prevent, it's one of the alternatives to prevent the vanishing gradient issue, right? And one of the things that happens when you have like such deep neuronal networks, such as the ResNet, right? So like, let me zoom out so you can see like the ResNet is much deeper than the VGGs, which is the architecture that we had discussed the most, right? So like when you have such a deep neuronal network, one of the problems that happens is that usually you get vanishing gradients too. So they figure out that if you manage to, if you keep summing what's the information that you had before and after that layer, actually you also prevent the vanishing gradient. So that was like inside the ResNet had. And then the Inception V3 has a workaround for that, which is this idea of parallel streams of information, like, and also helps with performance. So if you just want to see what's the comparison between them, right? So you see that, for example, the AlexNet, which is the model that we discussed during class. I don't know if you guys remember, right? In this image set data set, like it had performance 84.7%, right? Of like in the top 5 accuracy, which means like from like is the true label within the top 5 predicted labels as being the most likely labels given by the model, right? If yes, that's you say that like that was a correct prediction. So that was the performance, like 84%. The Inception was 93.3. The ResNet had higher performance, right? But look at the difference. The difference is that the ResNet, to be able to achieve such a good performance, had 60.3 million parameters. That's a lot of parameters. While the Inception, right, which was is smaller, right, but has all these like kernels running in parallel, managed to achieve good enough performance, 93.3 with just 66.4 million parameters. Like that's 10 times less parameters, which means that like less memory needs to be used and trains faster, most likely. Okay. Any questions with respect to the Inception? So like you see that the Inception is nothing else than like a different architecture for what we already have seen before, which is the convolutional neuronal networks, but just trying to take more information from the same stage in the process that you are, which like try to get information that's local, global, and how you can just combine that information with mixing information that's coming per pixel, but just from different layers. Okay. Any questions on that?
Yes, Antonio, this Inception, if you go back to this graph that you have done before, no, the one from the paper.
The one from
so
the paper.
Is this, yeah, the one that you just showed now. Yeah, below
This
the
one?
15. No, number 15, yeah. Where, so the Inception is the full architecture. No, I didn't get it.
The Inception is this. Yeah, the Inception is this. That's the Inception, right?
Okay.
So like the Inception V3 stands for like what's the combination of like kernels, layers, and max pooling operations that you do for that specific architecture. So this architecture has a name, which is Inception V3. Okay. So the same way how like we are discussing the AlexNet before, right, which is like also a different type of architecture within CNNs that had like a different combination of like convolutional layers, max pooling operations, and fully connected, right? The VGG16 and the 19, they're also CNNs, right? But you see that they have more layers. So for example, we don't do just like the AlexNet had convolutional convolution, max pooling, convolution, max pooling, convolution, max pooling, and then fully connected, right? You see that the VGG has convolution, convolution, max pooling, convolution, convolution, max pooling. That was the VGG 16. The VGG 19 has more. So like convolution, convolution, max pooling, convolution, convolution, max pooling, and then you have like sequence of 4 convolutions after that. Okay, so like you see that the names VGG, Inception, ResNet, it's respect to like how you make use of convolutions, max pooling, and fully connect. All right. What I was showing you here in this slide, that's one like the snapshot of one little block inside of the Inception. So like this block here is the equivalent of this block here. You see?
Yeah, this is what I want to know. Yeah, perfect. Okay, I get it.
Yeah, so that was just one inception layer, if you will. So like now you call this one inception layer. Okay, Mulitin.
Antonio, what's the purpose of this convolution one by one? I mean, this convolution one by one is just a multiplication of the metrics, yeah?
So remember that the convolution is done not just like for that one pixel, but the convolution is done over all the layers, all the like the stack in depth, right? So for example, although I'm doing that for just one pixel here, right? One pixel here, remember that this one pixel is a stack, it's a stack of like 77 layers, right? Which are described as the combination of these 45 different layers regarding land cover, right? And these 33 environmental raster variables, right? So when I do this one by one, I fix one location here and I do the mixing of all the 77 variables. So you see that like I'm combining the information that's in depth, not in space, when I do one by one convolution. Okay, so that was the idea.
So one by one convolution is actually 1 by 77 voxel element.
Yeah, right.
Okay, so we have 77 different coefficients. Okay, so like a linear combination of those. Yeah.
Okay. Yeah. Any other questions? So let's delete this. Okay.
So, Antonio, there was something about this punctual vector and punctual model that I didn't understand, maybe.
The idea of the punctual vector?
And punctual model.
Yeah, so like the idea is simple, right? So for example, one of the things that we discussed that could be done, right? Like if you want to make a prediction per pixel, right? Would be, say, let me move here so I have more empty space. So like imagine that I have this area that I'm trying to make a prediction for, like 64 by 64, right? Which is spanning over 77 variables, right? One way how I could potentially do a prediction if there is a species in that location or not would be to get the information that's spanning over all the 77 layers, right? So like export this location as being one big vector that's 1 by 77, right? If I have several like samples like this, right? Let's say that's like, okay, now I'm gonna sample several little squares like this over from all the maps that I have, right? Then I'm gonna have any of those, right? If I take this, you see that now I have observations by like features, right? And then I can have one more column here that basically represents, oh, let me switch back to content. Yeah, which would be like the species is there or not, right? So like, oh god. So if there is a species, so that's the ground truth information in the last column, right? So these would be the equivalent of using these punctual vectors, which like I'm just taking the information that's coming from that specific location, right? And associated directly to the ground truth information. How can I leverage this information that's coming from the 77 features that's being provided for that one location to make a prediction, right? And what they use as argument in favor of the CNN here is essentially that there is richer information in space. Great, I can delete it now. That there is richer information in space, right? Which is like what they attribute the better performance of CNN versus like other methods that don't take in consideration spatial information. Does it help?
Yeah, thanks.
Yeah, I'm going to stop sharing and share again so I can get rid of these lines. Okay. All right, so now we know what the inception is, right? They give like a couple of more details about the training, which like probably you guys are all familiar now. So like they said that they feed the model and they use cross entropy laws to train the model. So essentially what you have is gonna be like a ground truth where you have, let's say, a map that looks like this, where like here in red now it'd be like no species found there. So like no species for that specific species, because I'm assuming that they're doing that like per species in this case, right? And in ones here it'd be like where the species was found, right? So that's ground truth. And when you're gonna get from the model, it's actually like probability distribution. So like imagine that would be the equivalent of like some sort of elevation lines, right? Where here would be like highest probability and here lowest probability, right? You can compare those two in terms of like how much this distribution, which like model, right, resembles the ground truth distribution, right? And when you're talking about comparing distributions, that's where cross entropy comes in, right? As we saw before. Before we're comparing the distribution of labels when you have like several classes, right? But you can use exactly the same technique when you're talking about distribution of prediction in space. So like that's why they use cross entropy. Okay. Then next they say that they use stochastic gradient descent, which like that's one of the optimizers that we saw, right? They say that they use a technique for decreasing the learning rate. So like they start with 10 to the -1, right? And then they divide manually by 10 before a couple of fixed epochs, right? Which it's not very elegant, like raise several questions, right? Because like, how did you come up with that? Like, was that like, oh, you know what? Like here would be good to divide it against. Like that's not very elegant, right? If I'm the reviewer, I'd raise some questions about that. But we do know a couple of methods that do take care of that for us, right? You guys remember some of the optimizers that adapt the learning rate that we discussed? No one?
Was that was Adam one?
Yeah, Adam was one of them. I said that Adam was my favorite, right? We saw RMS prop, right? So like Ada grad, we saw Ada delta too. So like all of them, they take care of like adapting the learning rate for you. So like you don't need to do this division manually, right? Like that's kind of brutal force. Okay, so like yeah, that's weird that they did that, but you see that the goal is still the same. Like just try to find a way to decrease the learning rates as you get closer to the point that you want to stop, right? Where you believe that you have reached like what's the closest to the global minimum. Okay. They say that they use dropout, right? Like dropouts of 0.7. So like that's the probability of a node being present. So like in 0.3% of the case, you're gonna get that node removed from the network, which we had seen. They also say that they use momentum, which is important, right? Because after all, if you don't have momentum, you're prone to getting stuck in local minimums, which is like one of the things that you saw with respect to stochastic gradients, right? So like that's a smart decision that they made there, which is to add a little bit of momentum. We processed the validation every 5 epochs, and the final model was the one that had the highest validation score. Yeah. So yeah, So that's essentially how they managed to find the model that they were going to use, which like after all these variations that they have done, the one that had the best validation score in terms of like predicting the probability distribution for the species. Okay. So the training is quite clear, and that's basically what we have discussed in the lectures, right? So like I hope you guys thought that was very easy and like, oh yeah, I know all these terms that they are using there. Okay, so like now with respect to performance, right? So like they do comparison to a couple of methods. So like that's the CNN, like in green, right? That's the method that they want to use. The DNN would be the equivalent of the method using just the punctual information, right? So like that would be what we discussed of like getting each position over the 77 features, right? And try to predict what is the probability that I find one species in that location, right? So the difference between the two, the CNN and the DNN, is that the CNN is accounting for the spatial information, which that was their hypothesis. That's like including spatial information actually improves the performance of the model, right? Versus just doing the prediction like punctual for one specific location, but still using all the 77. So that's probably was a request from the reviewers, right? Because like if you're trying to claim that CNN is better because it's spatial, right? So like you have to show that like the punctual, which is the DNN, doesn't do as well, right? So probably that's why they add the DNN. And they say that the two models had the same architecture. So basically have like same architecture is not the right word, right? Because convolution cannot be compared directly to like fully connected layers, but probably they're talking about number of parameters, right? Like how big were the two models? Like probably they had similar number of parameters. And then what they show is that like from the models that they have used, which was the random forest in red, right? So that's random forest. This is boosted tree in black. Then in blue, you have just like the feed forward deep neuronal net, right? And here the CNN in green. You see that as you keep increasing K, where K stands for like what's the top K occurs. So for example, if you restrict the model to just say like, for example, the top 5, right? Is my the prediction that I get for that pixel, right? Is that correct according to the top 5 predictors that I'm getting, right? So like you see that the prediction is a little lower here. And as I keep increasing, like what's the degree that I'm willing to consider that the performance is still correct, I tend to converge to higher and higher accuracy, which like here borders like 0.35. Okay. Okay. Any questions with respect to that? So yeah, if you have any questions before we move on to the next paper. Vivek, is it sort of clear now, like what they are doing this paper?
Yeah, at least now I could like get sense of the the fancy words that I was not used to before. So like yeah, but I just had a question. Hello.
Yeah.
So if I have to run something like this, like is it possible to in my computer, or do you have to rely on like heavy machine?
No, the Inception V3 is actually pretty small, right? As we saw here. So like the Inception V3 is quite small, 6.4 megabytes. It's like you can do that in a laptop if you want.
Ah, okay. Thanks.
Yeah.
May I ask what is the 6.4 million means in terms of like the past model that we like the table, like the 62 million, 138 million for the like for the exercise that we did on Jupyter Notebook. Right? Is there somewhere that we can see how many parameters are included, or what?
So essentially, the number of parameters here stands for how many weights you have in your network, right? I can include one function that counts that for you, if you guys want, and then I can send that like via email. It's a very simple. So the input of the function, basically, like you create this function f that I can send to you, and you give as input the model that you created. So that would be the CNN or the the feed forward net that we discussed, right? And then you can count how many parameters you have inside. I can do that for you.
So maybe like or if it's like a one layer, it's 256 neurons, then that would be 256.
Right. Yeah.
And
If you don't
Antonio,
have bias, right? Yeah.
and of course, more there are these number weights, more complex is our network, our, you know, not the network, because the relationship between the variables, the predictors, isn't it?
Yeah, but it also depends on the architecture, right? So for example,
right,
if
yeah.
let's say
If
that
you increase, if you
yeah,
increase the hidden layers, you will have more weight. Yeah, of course.
Yeah, if I just increase the hidden layers, right? Like let's say that I have just 2 neurons per layer, and I have like 6 million parameters, but I only have 2 neurons per layer, no bias. That's basically stands that like I have 3 million layers. Like you're not gonna be able to do much with that. Although you have like the same number of parameters, right? Yeah. So the architecture matters a lot still. Which was essentially like that was the point of the inception, right? It's just say like, oh, look, the VGG net had like 138 million parameters, right? And we have just 6.4 just with a smarter like architecture, right? So like we have these parallel kernels going on now, right? And we have like a performance that's already better. So yeah, to show that like the architecture matters more than just the brute force number of parameters. It's like a clever architecture. Okay.
Okay, any other question?
And is it possible to run this inception like model in PyTorch library?
No, yeah, in fact, the inception was developed by Google, right? So the official implementation came out in TensorFlow, right? So that was not in PyTorch. But I think by now, like inception is such a classic method. I'm almost sure that you're gonna find implementation in PyTorch as well, where you can just load. There are several places where we haven't discussed that though. But for example, in PyTorch, you have model architectures that you can just load, right? And then do the fine tuning. So like you can load pre-trained models like this VGG, these classic methods, most of them, they're already available like for you to load directly from PyTorch, right? Then you load the architecture and you just do the training. So you give like, instead of specifying what each one of the layers are doing, right? You load a class that's called inception, right? And then the class now you do model equal inception, and then the model knows like, oh, okay, great, yeah, so that's the architecture that they should have, and then you just fine tune it. Yeah.
Yeah, thank you.
All right.
Okay.
If no more questions, maybe we go for the last paper. So who was presenting the last paper? Was that Charlotte?
Yep, that was me.
Okay,
Okay,
perfect.
cool. I'm
let's try
gonna
to
give
finish
it to you so you can.
Yeah, to 7:30. At 30, in this way we have 50 minutes to wrap up the course.
Okay, I'll make this quick then. You see my screen okay?
Yes. Yeah,
Okay.
make bigger like before.
Yeah. That better?
Yeah, that's better.
Okay. Yeah, so the study area for this paper is the Hamoon wetland complex. Hopefully I'm pronouncing that correctly. It's a large, locally important wetland complex near the border of Iran and Afghanistan that has seen a lot of degradation over recent years by a combination of drought and also increased water consumption driven by changes in surrounding land cover and land uses. in the case of this area, it would be great to restore all of the wetlands to their normal functioning, but because this is a water scarce area, there's not enough to do all of that. So the authors wanted to perform a prioritization study to see what would be an appropriate way to prioritize allocation of this limited water resource to prioritize different parts of this wetland complex. And they did that by dividing the functions of the wetlands into 4 distinct categories. The first one being reducing the negative effects of dust storms. They also looked at providing habitat for waterfowl. The third main function was providing socioeconomic benefits for the local economy. So things like supporting fisheries, farmers, shepherds, people's livelihoods. And then the last main function was providing water as a source for life in general. So they turned each of those 4 management goals into a different input layer and then put that through a multi-layer perceptron neural network. That's the high level explanation of it. Yeah, I don't know if there's any more details that would be helpful to cover.
I think we can ask the details like as questions arise. So, but thank you. I think that's a good intro. Thank you. And so now I'm gonna share my screen.
There we go.
Okay. So yeah, so she already like gave the general the idea of the paper, right? Which is like to determine the best areas for wetland restoration. And the authors do say that they use a multi-layer perception neural network apply to try to like that was the part that was less clear to me, is that like basically what they have, it's already this wetland restoration priority that's given by these specialists, right? They say that that's the priority map restoration given by WLC, which I assume is this organization, right? That's basically saying which area should be restored, right? And then in combination to that, Charlotte mentioned, you have this information that's coming from these other variables, right? That they are going to input as well. So you see that this is basically a regression task, right? Where you're trying to give like what's the index of priority that you're trying to approximate, given what the experts say, okay? Extremely simple. And then now with respect to like the architecture, right? So they say it's a NLP, neural network, was applied to prioritize the different parts of the wetland. Okay, so like I hope that at this point when you say MLP, like this architecture immediately comes to mind. The representation per se is slightly different from like what we saw before, right? So like they represented the input information in terms of P, right? So like it's P1, P2, all the way to PR, right? Those are the weights. So those are the connections that we have seen over and over again. The sigma here stands for like the weighted average, right? Because you have a weight for each one of these income connections that you have for this specific node here. Then you have this F, which is the node linearity, right? And they do say in the paper, I think I didn't write here, that they were using sigmoid, right, for that. So like the sigmoid was the activation function. So they are mapping the output to be between 0 and 1, like for each one of these regions. Okay, and that's the general function, right, that we have seen over and over again, where P now, like I usually write X, so they put P, but W is the product of like the input P with the trained weights W plus a bias that they represented here, right? Although they're sort of fixing the bias to be equal. I know it's 1 times BS. Oh yeah, B1, B2, and okay, yeah, so that's right. So then there is a trained bias. And then you have the A, which is the output for each one of these nodes. Okay. This study used a network containing 1 hidden layer and 15 neurons. I think that's extremely small, right? Although they say that they managed to get good performance with it, right? But like that's extremely small network, just 1 hidden layer and using just 50 neurons in this hidden layer. Very small network indeed, okay? They give some other details about the methods, right? Like what they're trying to approximate and so on, which I already have discussed. There is one thing that I thought was interesting. You see that they say that the neural network was trained using this method, Levenberg-Marquardt algorithm, which is more powerful than the gradient methods. So like, remember that all the methods that we have discussed so far, right? Like all the networks, they're all using gradient methods for training, right? So like, I thought that would be interesting to discuss essentially what this method stands for, like very in just few words, right? Very well. So like, you guys are very familiar with this formulation at this point, right? So like here, what you're doing is to compute the gradients, right? That you obtain. The gradients, essentially, they are like the partial derivatives of how the error is conditioned by the weights that you have for the current interaction, right? That gives you the gradient. You multiply that by learning rate, and then you modify what's the current set of weights that you're using to the next iteration. And then you keep like doing this process over and over again, right? So that is what the gradient stands for, right? If you guys remember the gradient, like if you're looking at a curve like this, right, where this is the error, right? The gradient essentially stands for like computing these first order derivatives along the curve, right? Basically, they are the slope of the curve that's touching the curve in just one point, right? So this is first order derivative. So you see that this doesn't tell you much more than like what's the direction of like decrease or increase. So like that's just a very linear approximation that you have there. Another alternative is that if you have the curve there, you can compute the first order derivative and you can compute the second order derivative, which essentially stands for like how fast the first derivative is moving, right? So like how fast, like between neighboring points, how fast the first derivative is moving. So that would be, if this is the first order derivative, right? Then you have the second order derivative, which basically is dx dy, if you will, which is the derivative of the derivative itself, right? And it has a name, which is like the Hessian, okay? So this is the Jacobian. Just so you guys know what the name of things. This is the Jacobian, which is like this first order derivatives, and this is the Hessian. The Hessian gives like how fast the curvature, like for example, in this case, is changing, right? So like that gives you like global information, if you will, about the loss landscape. So that's just not local, okay? Of course, the Hessian is complicated because like now I have to compute the derivative of the derivative, which like is computational expensive, right? So like when the data it's not that big, so like for small data with like small networks, indeed the Levenberg-Marquardt actually becomes like a viable option, right? Because then you have information about the curvature, like global information about the loss landscape. And that's here basically I'm describing like how these steps they look like. You see that you have intermediary steps there. This D here will represent what's these derivatives, right? That you have. That would be the approximation of the first order derivative. And the Hessian is this second order, if you will. So like it becomes essentially a product of the first order derivatives. That's a linear approximation of the Hessian. And then you have these other updating rule here that now instead of taking the gradients like we had here, actually you take the Hessian as input, okay? But of course, like this works for them because they're using a network that's just one hidden layer with 15 neurons. So like that's a very small network. So like then it becomes a viable option. For all the other networks that we have discussed so far, right? Like ResNet, Inception, like BGG, like and so on, right? You cannot afford to use the Hessian, like you cannot use Levenberg-Marquardt. So you do have to use the gradient descent, okay? But just so you guys know that there are other options out there besides gradient descent. Any options with respect to that? Sorry, any questions with respect to that? And then the results, I guess, right? So like this was the map that was given by the experts, right? And this is the approximation that they managed to get here on the right. So like essentially what they did here was to increase the number of priority regions, right? But you see that the two maps, they overlap quite a bit, I would say. I'm not entirely sure like what was the actual gain of this paper, to be honest, like besides getting more priorities, but like they're trying to approximate something that already looks like the experts, right? So maybe like, okay, we paid the experts this one time to get us this map, right? From now on, the experts, they're no longer needed. So like now we have the model that can keep doing the prediction. Maybe that was the point, but that was not entirely clear from the paper. Okay.
Maybe Charlotte, you can add something for this comparison. Do you get
Yeah,
something
I actually had the
more?
same question as Antonio. I mean, the way that I interpreted this paper is it tried to explore use of a neural network as an alternative to the normal method that prioritization studies are usually done, which is, you know, the weighted linear combination that was used as the target data set here. But I'm not sure if the way the data is presented actually helps to make a decision about whether the neural net adds value in combination. So I was wondering if there's an alternative experimental design that might have been more helpful for answering that question.
Yeah, because the way how it is, right? Like they don't provide any more insights than what the experts did, right? So like they're just replicating what the experts already did. So maybe this study specifically, the one that you're seeing here, is basically just like a validation case where they're saying like, look, we can approximate what the experts already do, right? And if that was the goal, now we have a model that basically learns like what are the combination of variables that usually matter the most when you're trying to estimate what's the priority of a wetland to be restored, right? And basically that's where they stop their study there. I don't remember if they follow with anything after this. Let me see. No, yeah, that was the last slide. So like, yeah, I think they stopped there basically. Yeah, any questions?
Yes, how do they show that these two are matching? Is there like a R squared or an accuracy based on the model and the ground
That's a
truth?
great question. Well, let's take a look there. But I don't remember seeing anything like that.
Because just from the diagram, it feels a little bit different.
Yeah, I mean, this paper was not great. Yeah. Yeah, here. The RMS of the trained model is 0.04. Yeah, but like they're not comparing to anything, right? Like they're just saying like, yeah, that's the RMS with respect to the ground truth. So like we did a mistake by this much. Like, what does it actually mean? It's very vague. Is it doing better than other methods? Like they don't really do this comparison. But yeah, visually you can see that like, yeah, basically they're obtaining exactly the same information that the experts did, right? Like all the regions they were overlapping. Yeah, but this is, yeah, multi-layer perceptron, you know, like extremely simple, just one hidden layer, 15 neurons, you know, like people use that for things. So it can still give you like some insights on your data. So don't underestimate the importance of like small models, I guess. Okay, I think that was it from my end. Yeah.
Yeah, thanks, Antonio. Any other question in these regards? Probably not.
One more question is that how do we
yeah,
decide how many hidden layers should we choose? Should we just, or like a grid search, just also like a 1 to 10, and then maybe 1 is the best, and then use the 1 as our final model? If we are doing similar case study.
The question was how to choose the architecture of the network?
Like the how many, like for example, for this kind of a simple model, if we are doing similar cases, how do we choose the number of layers? Should we?
Yeah, that's a hyperparameter tool. Yeah. So like you try different numbers of layers and you see which one is performing better. Like sometimes you come up to like very weird conclusions. Like I was discussing that with a student of mine this morning, you know, like he was showing me like the performance of a model that he was training. And like the intuition was like, okay, we're doing something that's similar to what the chat GPT is supposed to be doing. So like, let's use a model as big as they do, right? And then the model was performing bad. And then like for debugging, we said, oh, you know what? Let's decrease the size of the model. So like ChatGPT is using like 50 layers with like millions of neurons in each one of these layers. Let's do something smaller, like 2 layers, you know? And actually 2 layers performs much better. And then you're like, oh, wow. Like, and then now you're trying to understand why that's the case, you know? And like one of the ideas is that like, because the other model, the original one that we're trying was like so large, right? You had so many neurons in there. Basically that model was memorizing the whole data set, right? And when you apply it to like an actual unseen data set, then it performs poorly. Remember that figure like that I showed for the overfitting? When you have like such a complicated function, it managed to get like 100% of accuracy in the training set, but fits a function that basically just doesn't follow the trend of the data at all, right? So that's overfitting. So like the large model was overfitting after all. So sometimes a smaller model, it's better, and that's the sort of insights that you gain when you play around with hyperparameters, right? So like the screening for hyperparameters is always very important.
Okay, so we come up to this ending of the last 15 minutes of the lecture. I want to just briefly do an overview of what we have done in the course. So we have covered up all the geocomputation part from dealing mainly with the raster data set with vector data using all the GDAL and PK tools. And there is another software very powerful in the geographical space that is GRASS. Once again, I didn't cover, but there are video lectures in the spatial ecology webpage. And then we, when we were able to treat all the data set, the geographical data set, and arrange all the, pixel and so on, and raster and buffer and whatever we want to do it in the geo dimension. Then we went inside to we created a table, and we went inside to the machine learning for mainly covered by Antonio with the neural network. There are plenty of other techniques of machine learning also we didn't, for example, fully cover all the variable selection procedure that are over there. There are actually one lecture from Antonio. It was Shapley. It was the library for doing variable selection, Shapley, something like this. Shapley, yeah, from Shapley. And you can find a video recording from last year for variable selection. So as you have seen in this course, we need to tweaking a bit our mind in the context of big data. Okay, the geocomputation, the geographical layer have big data, but quite often people try to summarize them and working with a small study case, little study area, because they don't have the capacity to go big from the geocomputation part and also from the modeling part, from the complex modeling part. Okay, so try to break this barrier at least in the thinking first, and then in the application, because the application and the tools are there. Is what we teach you guys from both geocomputation and machine learning part. So you need to first think in this multidimensional way and in the vast geographical space in order to achieve your goal with this new technique. Okay. Quite often I see all this paper, you see that the Antonio covered up the machine learning part and was quite straightforward model. And the geocomputation probably is something that we can do in 2 days. The China example can be done for the full China rather than for 3 cities. It's not a big deal, especially when you know the tools and you get used with all the tools that we have been teaching so far. We, as I mentioned in my email, for the final project is going to be compulsory for the people that wanted a certificate from spatial ecology. Later on, you can, if you need, you can request a sort of certificate also with the number of hours that you spend in the course, and also with the self-study that we try to estimate in order to get a credit from your university. We can't release the credit because we are not an academic institution, but we can release a certificate with the number of hours, and then you can request your university to get approval. Okay, both of us are me, Antonio, we are academic, so also this one can be useful in this context. Peter and Francesco, they are not academic because they work for research center, but they are still scientists in this aspect. So eventually they can be part also of the certificate screening procedure if your university has it. So for the, once again, for the presentation, we are going to have it in Matera in the Thursday and Friday. So please, especially for the people outside to the Matera event, send us when you can present in according to the, we were running from 9 to 5 p.m. Eventually we can arrive to 6 if something has some issues. So, and there is going to be the Thursday and Friday, in particular the 8 and 9. Okay, so I've been reported already in the email these dates. So that's it. We always open the courses from the people from next year. If somebody has been participate, you can follow up also the next year if something was not clear, or you want to review stuff, or there is something new. More or less 80% is the same, but we try always to keep update. It also is a way for us to learning something new in this aspect and respect. So I want to say really thanks to Antonio that has been really try to simplify as much as possible the neural network science behind the math procedure. I think you really reach a good balance between the depth of maths and the application part. So that, as you can see, are important to understand. And then when you read the paper to understand what is ReLU and why it works, activation function. So you need a bit of this background for understanding the neural network. So Antonio is going to come is going to stay all the week. Rather, Peter and Francesco, they will come for a few days. For the people remotely, we will try to have a connection going on for the full day. So feel free to asking us to have a one-to-one session also for the people abroad, and we will organize the time, and we will have an open connection with Zoom, but can happen that sometimes we are busy, so try to call us, let's say, to pay attention also to you. So we will do our best in having one-to-one conversation with one remotely. That's it from my side. If there is any question on this final part. And one more thing, so I'm going also to sending a link for the final questionnaire about how we performance, what can be improved in the course, and so on. That is always useful to see and to improve next course that we are going to running next year. We always look for people like Antonio, like Peter, with everyone that is willing to participate next year as a teacher. So if you feel comfortable in teaching something, can be also 1 hour, 2 hours, feel free to join, to reaching us, and we will try to accommodate your willing to participate also as a teacher. And you can also participate again to the maybe if you didn't have time to come to Matera, you can come next year free of charge. So we try to keep a sort of ongoing procedure also for the people that have been already participate. That's it from my side. Is anyone has a question on this aspect?
Let me just say one thing, Joe. It's
Yeah,
like,
please.
yeah, we cover like some content that usually I cover in the span of 6 months, right? So like we did that like in basically just 6 lectures, right? So I overlooked a bunch of details and we try to like just give like the big picture of most of the things. But if there is anything that's like to learn more about that I didn't talk about like in the class, right? Which definitely there are a bunch of things that you guys still have questions about, feel free to email me and I can definitely point you towards like more resources, right? So if you're more interested like on the mathematical part, right? Like I know that a bunch of people had more questions about the actual theoretical guarantees that the things they work, you know. So like those things, feel free to email me and I'm gonna try to help you with like extra resource. And if you don't care about the math, you know, like at least I hope you manage to get an idea of like why is it important to understand the overall concepts, right? Like the building blocks that makes these large neuronal networks, because it's by knowing what you need to change specifically in this architecture is basically what tells you apart from like having a poor performance versus having a decent model, right? So I hope at least that I managed to teach you guys. Okay. And thank you for the participation. I really enjoyed very much like all the questions that you guys asked.
Okay, thanks, Antonio. Okay, anyone want to say something about this? Everybody quiet, come on. Even the last moment.
I just want to say a big thank you to Antonio and Giuseppe. The past 3 months, past 2 months, it's been really helpful for me. Particularly, I don't have a strong coding background, but brought me a lot of new insights and new enthusiasm to working on code. And I hope to learn more in the following weeks in Matera. Yeah, very excited.
Okay. Yeah, the video lecture, there are always open, so you can see also the one from last year. So feel free to go through the video recording, and going to put all these video recording that we have done so far also in YouTube. So it's going to be open without password and so on. So give me, probably I will do it during the summer, we'll transfer everything to you. But the syllabus with the link will be always there as it is now, but without password. So that's it. Any other input from all the people over there?
Say thank you, Giuseppe and Antonio, for all this thing. Yeah, it's been really like amazing. Yeah, like for someone like I have not so much of well background, so at least now I feel at least comfortable of like dealing with these things, and then yeah, well hopefully I can like try to bring this knowledge into the project, like I will try to build. So yeah, thank you so much.
Yeah, thanks, Vivek. Yeah, so go back. The video will be there, so go back and listen again. Also, because sometimes, I mean, we forget stuff, so it's good to have a kind of a review of these lecture from time to time to see what is going on here. Okay, so I think we can close. I'm waiting your email concerning the time frame that you want to present, especially for the people outside. People coming to Matera, we can arrange when you are here. And that's it. And people from Matera will follow with them with specific about logistics and where we are going to meet and so on. And that's it. Okay. See you online. See you in Matera. See you during the video call for the project presentation. I hope many people present. Okay. And if you have any issues or you want this kind of supervision, let us know.
Okay, bye everyone.
Okay.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you.
Bye.
Bye.
Thank you. Bye.